Welcome back. In the previous class, we had derived the momentum balance equation vectorially in a compact form. It's dou dou t of rho v, which stands for rate of increase in momentum per unit volume, equals minus of del dot rho vv, which is rate of gain in momentum by convection per unit volume, minus del dot tau, rate of gain in momentum by viscous effects per unit volume, minus del of P, which is the pressure force on the element per unit volume, plus rho G, which is the gravitational force on the element per unit volume. Okay. This is a short form way of representing, or a vectorial way of representing these equations, which we are more familiar with in terms of the components in various directions. This entire set is compactly written in that one equation that we saw earlier, that we saw just before. Okay. See here, you have rho Vx Vx, rho Vy Vx, rho Vz Vx, rho Vx Vy, rho Vy Vy, rho Vz Vy, rho Vx Vz, rho Vy Vz, rho Vz Vz. Therefore, there are 9 terms here. Similarly, there are tau xx, tau yx, tau zx, and so on, 9 terms here. Okay, and this has been represented as del dot rho vv. This is neither a dot product nor a cross product. Okay, this is a dot product, yes, but vv, what is this? This has been written this way to represent these 9 terms here, right? So remember this, I will talk more about it. Similarly, this tau again represented these 9 terms here. Okay, this is called a tensor. A tensor is represented as this. This, as we come to know, is also a tensor. This is a second order tensor. This also is a second order tensor. A vector, a column vector typically that we use, or a row vector, is a first order tensor. Okay, tensor is a more general term. And these two were quite straightforward. Del of P and rho G were quite straightforward. So let's talk a little bit more about these new vectorial quantities, tensorial quantities that you have been introduced to as a part of this derivation. Let's begin with that. So as we saw, the shear stress has 9 terms. The shear stress tensor tau squiggle hat has 9 terms. So tau is the second order tensor with 9 components that can be represented as tau tensor equals in a matrix form. We typically write the components: tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, tau zz. Okay. Please see the appendix 1 of your textbook for a nice development of this. I've told you many things here itself. If some things are unclear, please check the appendix. As I mentioned earlier, VV is a new concept. There is no dot here, there is no cross here, right? It's not a dot product, it's not a cross product. But this VV has resulted in 9 terms. Okay. So in other words, we have represented those 9 terms as V vector written together. Okay. So this is a new quantity. It's called the dyadic product. And it's a special form of the second order tensor. For example, a dyadic product of 2 vectors V and W, that is Vxi plus Vyj plus Vzk, plus Wxi plus Wyj plus Wzk, if these are the vectors that are being considered, then Vw, the dyadic product, is nothing but Vx Wy, Vx Wz, Vy Wx, Vy Wy, Vy Wz, Vz Wx, Vz Wy, Vz Wz. Okay. So this is the representation of this. This arose in our manipulations, in our derivation, and this is called a dyadic product. This is known as a dyadic product. Again, if you are unclear and for what algebra or what identities are valid for this and so on and so forth, please check the appendix. Okay. You already know that you need to treat vectors differently from tensors when they are written in a compact form. When you write the components, they are just scalars. Okay, the components are scalars, so they are just numbers that you can manipulate in the same way. But when you compact them and write it of a vector form, and you compact them and write it of a tensor form, there's a certain algebra that goes along with it, which needs to be consistent with what you get when you expand those various components and do manipulations on those components. So that's the reason why a simple algebra that you do with numbers may or may not be valid for the vector algebra. There's a separate algebra for vectors and you need to pick that up. You would know, you would have done some vector algebra as a part of your initial math course. This gives, the appendix 1 gives a complete set of manipulations as needed by us. That is, it's not comprehensive. It's as needed by us, whatever vector algebra is needed, tensor algebra is needed, is given, is actually developed in that appendix. Please go ahead and see that. Okay, let us rewrite equation 3.4.1. Okay, let me get back to the laser pointer here. Let us rewrite this equation. What is this equation? If you see here, this was equation 3.4-1. Okay, so this is the momentum balance for the x momentum, or momentum in the x direction, the momentum rate in the x direction. So here we have, as I mentioned earlier, a function of a product of three functions, a product of which we need to take one at a time to be able to directly use it, or it might be much easier to directly use it. So let us simplify that, and as you'll see, it gets simplified significantly. So let's get back to where we were. Yes. No, this we have seen. Yes, this. So dou t of rho Vx plus dou x of the product of rho Vx and Vx plus dou y of the product of rho Vy Vx plus dou z of the product of rho Vz Vx equals minus dou x of tau xx plus dou y of tau yx plus dou z of tau zx minus dou p dou x plus rho gx. Okay. We're going to expand this term essentially as well as this term. This is a product of two functions, this is a product of three functions, all of which can vary, none of which is a constant. We haven't assumed any constancy of density or anything like that to make it generally applicable, because a gas, the density can vary, right? So if we expand the left hand side, this side, first this first function rho into derivative of the second function dou Vx dou t plus the second function Vx derivative of the first function dou rho dou t. So this is done. Now let us take two at a time first and then leave out one. We'll consider rho Vx as one function and Vx is the other function, and then we'll go ahead and expand the product of two functions in the next step. Let's go step by step. Okay. So this is rho Vx dou x of Vx plus Vx dou x of rho Vx. Okay. So that's how this expands, plus rho Vy dou y of Vy x is remaining here, dou Vx dou y, plus Vx dou rho Vy of dou rho Vy dou y. That is these two terms for this term, and this term expands to rho Vz dou z of Vx plus Vx times dou z of rho Vz. We are just taking to the left hand side for now. Okay. Let's recombine the terms to see whether we get something nice out of it. We'll get something nice out of it. Rho dou Vx dou t is fine, plus Vx dou rho dou t, that remains the same. Now let us pull Vx out alone from wherever it arises separately. So you have a Vx here, you have a Vx here, you have a Vx here. So if we pull that out, you have remaining dou rho Vx dou x plus dou rho Vy dy plus dou rho Vz dou z, that is this term. The remaining terms, let's combine to rho Vx dou Vx, rho Vx dou x of Vx plus rho Vy dou y of Vx plus rho Vz times dou z of Vx. So that gets combined into this term. Now let's expand this product of two functions. This remains the same, the first two terms. This is Vx, of course, remains outside. First function rho, derivative of the second function dou x of Vx, plus the second function Vx, derivative of the first function dou rho dou x. You get the idea. So you get the other terms plus rho dou y Vy plus Vy dou y of rho plus rho dou z of Vz plus Vz dou z of rho. Plus this term, I'm just pulling out the density out common, Vx dou x of Vx plus Vy dou y of Vx plus Vz dou z of Vx. Now let us combine this in a slightly different fashion to effect some simplifications. A lot of simplification happens. I'm just keeping Vx dou rho dou t here and combining rho dou Vx dou t along with this term. Okay, you see why I am doing this, because dou Vx dou t plus this is nothing but the substantial derivative. Okay, density is outside here. So let me combine this with this to write this as the substantial derivative, rho dou Vx dou t plus Vx dou x plus Vy dou Vx dou y plus Vz dou Vx dou z. Okay, this is nothing but capital D dt of Vx, and of course there's a rho here. These terms, of course, this remains from the first two terms, Vx dou rho dou t, plus let me pull out rho Vx. You know, Vx is here, rho is here. So this term, and this term together. Okay, so rho Vx times dou Vx dou x plus dou Vy dou y plus dou Vz dou z, that gets combined into this. And if I pull out Vx here, there's already a Vx here, I'm just writing the other terms as it is. So Vx dou rho dou x plus Vy dou rho dou y plus Vz dou rho dou z. So that accounts for all the terms of this. Okay. So as I mentioned here, this last term is nothing but rho substantial derivative d dt of Vx. And let me call this entire thing here as E. Okay. You'll quickly see why I say so. Do you see a form emerging here? Dou Vx dou x, dou Vy dou y, dou Vz dou z, and so on. Okay. Take a look at this. E is just this. Now, when we use the equation of continuity, the complete form, d rho dt equals minus rho del dot v, right? So the first term on, I think that's the, we are looking at the left hand side. The left hand side of the equation, well, we use equal to whatever, left hand side, right hand side, that's only side that we are looking at, can be written as the negative of the second term on the right hand side. What I mean by that is, you have Vx minus dou Vx dou x plus dou Vy dou y plus dou Vz dou z. Okay. And this you could see is nothing but del dot v. Okay. So this minus del dot v you have here. Here you have dou Vx dou x plus dou Vy dou y plus dou Vz dou z. And you have a rho Vx term here. You have a minus rho Vx term here. So using the equation of continuity, this becomes the negative of this and they cancel each other out and the entire E goes out to 0. Therefore, you could write equation 3.4-1 as rho substantial derivative d dt of Vx equals whatever terms that remain here. The left hand side has just become this now, and you have the right hand side of the original balance equation on the x direction, momentum balance, minus dou x of tau xx plus dou y of tau yx plus dou z of tau zx minus dou p dou x plus rho gx. And you could express the other components just by extension. If you don't believe me, you can go back and rederive the whole thing for the y direction alone, for the z direction alone. You will find that you will end up as extensions of this. You will have to write the appropriate indices and you will be fine. So if you do that and you express it vectorially, you would get rho d dt of v equals minus del dot tau tensor minus del of p plus rho g. Okay. So equation 3.4-5. This is nothing but mass per unit volume density. This is the acceleration, okay, in a certain view. This is nothing but the viscous forces on the element per unit volume, on the control volume per unit volume. This is the pressure force on the element per unit volume. And this is the gravitational force on the element per unit volume. Okay. Now, if you use the equation of continuity, we can write the substantial derivative of rho with respect to t as minus rho del dot v. That's what the equation of continuity tells us, general equation of continuity. Then with no assumptions here. So the first term on the right hand side can be written as the negative of the second term on the right hand side. Okay, what I mean by that is E is nothing but Vx times minus rho dou Vx dou x plus dou Vy dou y plus dou Vz dou z plus rho times Vx equals dou Vx dou x plus dou Vy dou y plus dou Vz dou z equals 0. Okay, so this is what our thing in the flower brackets was, and this can be written as rho. This is the only term that will remain here. Okay, because this can be written as the negative of the second term. The first term on the right hand side can be written as the negative of the second term on the right hand side, and therefore E becomes 0. Okay, the E first term on first term is nothing but the negative of the second term. Using the equation of continuity, I'd like you to work this out and convince yourself that this is indeed 0, and therefore your equation of continuity becomes, equation of motion in the x direction becomes rho dvx dt substantial derivative equals minus dou x of tau xx plus dou y of tau yx plus dou z of tau zx minus dou p dou x plus rho gx. Okay. The other two components can be written as by extension. You put in the appropriate subscripts here, you will be fine, and putting them all together in terms of the substantial derivative, we can write the equation of motion as rho d dt of v equals minus del dot tau tensor minus del of p plus rho g. Okay. Equation 3.4-5, and this is nothing but mass times mass divided by volume density times the acceleration, and this represents the viscous forces on the element per unit volume. This represents pressure force on the element per unit volume, and this represents the gravitational force on the element per unit volume. So this is a nice compact way of writing the momentum balance equation. This is the overall momentum balance equation, vectorial momentum balance equation, a short nice way of writing all the terms that we wrote earlier for each of the directions separately. I'd like you to see tables 3.4-1 to 3. Have I shown you that already? No, I have not shown you that. Let me show you that. So see here, the equation of motion written in Cartesian coordinates. Let us focus on A1, B1 and C1 for the time being. Okay. So this is the expanded form of the vectorial rotation that we wrote. We have written it like this so that we can use it directly. We'll have Vx, Vy, Vz, we can use this one directly. Okay. So note that A1, B1 and C1 gave us those three terms that we derived. Okay. So that we'll come back to this in a little bit. Now, let's move forward. Let's do a few more things here. Let's try to understand a few more things here. Now, using the equation of continuity, which is, and I think this is what I showed you earlier. This is what we did earlier. Okay. We have this equation in terms of course, there's a velocity here, there's a shear stress, there's a pressure, and there is gravity. Shear stresses are not easy to measure. Okay. So if you have a handle on shear stresses, then you could use this equation, very general equation, valid all the time. Okay. If you have only the velocities, then we need probably a different form to be directly useful. Okay. So if our interest is in finding the velocity distributions, we need to substitute the stresses in terms of the velocity gradients and fluid properties. You already know how to do that. We have the Newton's law of viscosity that gives us the relationship between shear stress and shear rate. We looked at it in one dimension, we can extend it to 3 dimensions. So some relationship between shear stress and shear rate is needed to convert the previous equation, which was in terms of the shear stress, to an equation in terms of velocities. Okay. Of course, that would limit the applicability of the equation. Once you use Newton's law of viscosity, the equation that you're going to derive will be applicable only for Newtonian fluids. Right? That goes without saying. Whereas the first equation is applicable for any kind of fluid. Right? Okay, just remember that. But Newtonian fluids are so widely used that it's very useful to have an equation for Newtonian fluids alone. So let's do that. This is the Newton's law of viscosity, tau yx equals mu times minus dvx dy. And this again was for an initial understanding. This was only in 2 dimensions. Okay. As we can see, there are contributions of one to the other and so on and so forth. Therefore, the velocity gradients in probably two different velocity gradients could contribute to a particular shear stress, and so on and so forth. This could happen, and it is non-trivial. There's a paper that was published a while ago that has actually worked this out for Newtonian fluids, and they have come up with certain relationships between the shear stresses and shear rates. So this is only for an initial understanding. In 3 dimensions, the multiple velocity gradients would determine a shear stress, as I just mentioned, and equations given in 3.4, table 3.4-4 to 6 are the components of the stress tensor for a Newtonian fluid in laminar flow in the 3 coordinate system. So let's look at 1 coordinate system to understand that. I'll show you that. here we go. See here, let's just look at rectangular Cartesian coordinate system to begin with. You can see that the shear stress tau yx, okay, this happens to equal tau xy, but this is actually a sum of two different velocity gradients in 3 dimensions. Similarly, it happens for the other shear stress, the third shear stress, and the normal stresses are expressed in this complex form. We are not going to get into why it happens this way. This is non-trivial. Therefore, it's not a part of an initial course. You can go to that paper and check how this is derived and so on and so forth. It's non-trivial. Therefore, let's take it on face value for our purposes that tau xx is given in terms of these velocity gradients, tau yy is given in terms of these velocity gradients, and tau zz is given in terms of these velocity gradients. So this is the relationship between shear stress and shear rates or the velocity gradients in a 3-dimensional case. If we do this, if we substitute these velocity gradients and write our equations of motion, then we would get for the x momentum alone this relationship between the when you convert the shear stresses in terms of the velocity gradients. Okay. So rho dvx dt, the substantial derivative, equals dou x of 2 mu dou vx dou x minus 2/3 mu del dot v plus a term for the y direction plus a term for the z direction minus dou p dou x plus rho gx. So these would be the equations 3.4-6, 3.4-7, 3.4-8 for a Newtonian fluid, because when we looked at the relationship between shear stress and shear rates, that limited to a Newtonian fluid. In this case, you could have different relationships for different fluids. So these equations would be valid only for a Newtonian fluid. So these above equations of motion, these are the equations of motion, and the equations of state are the relationship between PV and T, or P as a function of rho, and the variation of viscosity with density completely determine the pressure, density and velocity components of a Newtonian fluid in laminar flow. Okay. Just remember this is for some sort of a big picture. If you understand that, it is fine. Otherwise, just keep it in your mind. At some point in time, this will become clear to you. Okay, much after you get into the field and so on and so forth. Just remember this. Okay. Now, when rho and mu are constant, since the equation of continuity reduces in such a case to del dot v equals 0, the earlier equations that we had can get significantly simplified. Okay. So those equations are widely used. Constant rho and mu are quite commonly encountered in a Newtonian fluid, a Newtonian flow, or a flow of Newtonian fluid, and therefore let's do that. If you do that, then the equation becomes nice and compact. Rho dv dt equals mu del squared v minus del of p plus rho g. Okay, this is a nice equation. This is for a Newtonian fluid, of course, not as general as the previous equation, but that's okay. It's very useful. This is equation 3.4-9. This is the famous Navier-Stokes equation for a Newtonian fluid in laminar flow and so on and so forth. That is, I mean, it's actually a limited equation. It's a very famous equation. Aerospace people use it significantly and so on and so forth. That equation is only a special form of the more general momentum balance equation. Now, if the viscous effects are not important, then the del dot tau term can be put to 0 because the shear stress is not going to come in at all. Okay. This is an idealized situation, not a real situation, idealized situation. which becomes useful in many analyses. And in such a case, your equation of motion becomes rho dv dt equals minus del p plus rho g. 3.4-10, this is called the Euler equation. Okay. So these are two special equations that come out of the equation of motion for a Newtonian fluid. Okay, I think we will, before I take a break, let me show you the equations and also the complete set of equations in this table. Okay, this will be available to you for download. So please make a copy of the entire set of tables here and keep them as a part of your notes. You have three equations of motion tables, 3.4-1, I think 3.4-2 and 3.4-3. The difference between these tables is the coordinate system. The first one is for rectangular Cartesian coordinates. The second one is for cylindrical coordinates. The third one is for spherical coordinates. The equation of motion in these three coordinates in terms of the individual components. Okay. For example, if you have cylindrical coordinates, you will have r, theta, z. Okay, r, theta, and z. And if you have spherical coordinates, you will have r, theta, and phi. Okay, so these equations are written in terms of those. The conversion has taken place already using the principles that are given in the appendix. And also, as we saw earlier, the 3.4-4 is the components of the stress tensor for Newtonian fluids in Cartesian coordinates first and for cylindrical coordinates next and for spherical coordinates. This you won't need too much. However, you will need the first three tables, 1, 2, and 3 of 3.4, and therefore please make a copy of all the 6 tables and keep it as a part of your easy access folder. Okay, keep it in your easy access folder. Hard copy, soft copy, whatever it is. Okay. So let us finish up today. We completed the discussion on the equation of motion, derivation, the understanding of the various terms, and so on and so forth, how they came about. And we did that because the equation of motion is much easier to apply in many different situations compared to shell balances for any situation, momentum rate in this case. In the next class, I'm going to show you the application of the equation of motion to various situations. We'll start in a few classes from now on. Over the next few classes, I'm going to show you the various applications. Okay. See you then.